Okay, let's dive right into this. Welcome to This Explainer, where we take complex ideas and turn them into clear, focused learning experiences. Today, we're literally opening up Unit 5 of our science material. And this unit, it focuses heavily on a fascinating, totally invisible world that's hiding right inside your own home, the wild world of acids and bases. We're going to be launching a full-on investigation into the hidden chemical identities of the liquids we use every single day. So, let's decode the chemistry of your kitchen, shall we? Which brings us to the central mystery of our explainer. How exactly can you tell if a liquid is an acid or a base without tasting it? I mean, in our daily lives, we're completely surrounded by liquids. Some are perfectly safe to drink, like water or orange juice, but others are meant for heavy-duty cleaning or industrial use. And since we obviously can't and definitely shouldn't taste or touch every unknown liquid we stumble across just to figure out what it is, we need a special, highly reliable tool. We need a way to make the invisible properties of these chemicals visible to the naked eye. Well, the solution to our little mystery is something called an indicator. According to our Unit 5 text, an indicator is basically a solution or substance that gives off completely different colors when it's mixed with acids or bases. Think of an indicator as our chemical detective, or even better, kind of like a translator. It takes that hidden chemical language of acid or base and translates it into a language we can instantly understand. Vibrant, unmistakable color changes. Now, you might be thinking you need a high-tech school laboratory to do this kind of serious science, but you really don't. Take a common garden plant, like the shoe flower. You might just see a pretty flower, but in the context of chemistry, it's actually a super powerful, completely natural chemical detective. The petals of the shoe flower contain natural compounds that act exactly like the indicator we just talked about. And the best part? We can extract these properties right at home to test the world around us. So let's see how this actually builds into a real scientific method. Activity 5.1 from our source material breaks this down into 4 incredibly simple steps. First up, you just boil the shoe flowers to prepare your indicator solution. Second, you take equal volumes, specifically, let's say 2 milliliters, of your suspect liquids and put them into separate test tubes. Third, you add just 2 little drops of your freshly brewed shoe flower water into each tube and give it a good shake. And fourth, the magic step. You simply observe. With just those couple of drops, those boring, static test tubes are about to totally transform. But before we reveal the results, let's formally meet our suspect lineup. These are the everyday household liquids we're testing in Activity 5.1. We've got lime juice, vinegar, soapy water, lime water, ash dissolved water, common salt solution, and finally, just plain pure water. Now, just hearing this list, I want you to take a second and mentally guess which of these might be acidic, which might be basic, and which ones are just perfectly neutral. Got your guesses? Okay, hold on to them. All right, here is the exciting part. The results of our shoe flower test finally reveal the true chemical identities of our everyday liquids. It turns out lime juice and vinegar are officially classified as acids. On the flip side, soap water, lime water, and ash mixed water fall squarely into the base category. And finally, our common salt solution and pure water, completely neutral. Our natural floral indicator successfully sorted these completely different-looking liquids into their proper scientific buckets. Now, the core scientific principle at play here is this really elegant rule highlighted in our source text. You'll observe that acids give one distinct color, while bases give a completely different color when mixed with the shoe flower solution. It's exactly this stark visual contrast that allows us to safely and accurately classify these liquids. Think about it. Without this color-changing reaction, a test tube of highly acidic white vinegar and a test tube of neutral pure water would look exactly the same to us. It's a real game changer. Okay, so what if we transition from our makeshift kitchen garden experiment into a formal school laboratory? Well, there, we rely on standard litmus paper. As our Unit 5 text points out, litmus is an indicator that is super common in science labs everywhere, and it generally comes in 2 distinct types, red strips and blue strips. So instead of having to boil flowers over a stove, scientists and students can literally just dip these incredibly convenient little strips of paper directly into a liquid to get their answers. In Activity 5.2, we're actually tasked with using these red and blue litmus strips instead of the shoe flower solution, testing them on the exact same liquids we looked at earlier. By substituting our homemade DIY indicator with these professional strips, we get this fantastic head-to-head comparison for identifying acids, bases, and neutral substances. By carefully documenting how the red and blue papers react to each solution, you're essentially creating a perfect mental cheat sheet for classifying chemicals in any formal laboratory setting. But hey, the detective work absolutely does not stop there. Let's take a quick look at Activity 5.3, which is all about extending our investigation even further. We can actually prepare other completely natural indicators, like turmeric boiled water, for instance. And we can test an even wider, incredibly diverse array of household items. Just imagine testing foaming shampoo, fizzy soda water, sticky sugar and glucose solutions, or even something harsh like kerosene. By applying the exact same methods we've just learned, you can classify pretty much any liquid you encounter. And that brings us to our final thought for this explainer. We've seen how simple, everyday things like a shoe flower or a bit of boiled turmeric can act as these amazing chemical translators, right? They turn completely invisible properties into bright, categorizing colors. So I'm going to leave you with this question. What hidden colors would the liquid sitting on your own kitchen counter right now reveal? The whole invisible world of acids and bases is right there, just waiting for you to test it. Thanks so much for focusing in with me today, and keep exploring the science all around you.